Well, thank you for coming
No, it's
to
my
the lecture.
pleasure. It's a beautiful place, and it's quite a week of activities.
Yes, it is.
Yeah,
It was very lively yesterday, I
yeah.
the report from upstairs.
You mean the activity outside or in the?
You're part of it. We've kind of stolen your climate festival. You see the take over there, Anders? See the Bolin Center things like we're stealing. We're stealing your lecture. You'll pick a fight with me later.
Yeah. No, it's beautiful, and a lot of good questions. Questions today and our earlier talk, and a lot of old friends here too. And the departments over there, Martin, Ned, Helen. Tomorrow we'll go talking. I hope they understand what I'm saying.
If you speak as you will be fine.
I'm going to ask them if they understand.
They probably will lie.
They will lie.
They will lie.
Oh, they lie.
They lie.
Be the nice guy.
No, don't be the nice guy. I like the nasty guy.
I'm not as kids love me. They look good.
They'll love you. It's all good.
Yeah. No, I'll have them ask the question. I don't mind being interrupted. I always. I'll tell them. If you see someone asking questions, I don't get it. I don't use those. No, I just don't use no. I mean, I've always used sides. I did for Twitter. No, they can. One is Patrick Burns or something. But I'll go. No.
Never.
No, he said I don't have to turn the switch on.
No.
You never thought you have a professor close setting up your own. A month later, no, but I brought the board, so I just lost one. I never got it.
So if the last people could take their seats. Thank you. Good afternoon. My name is Cynthia DeWitt. I'm a professor at the Department of Environmental Science and Analytical Chemistry here at Stockholm University. I'm also the chair of the Bolin Center for Climate Research. And I'm also here to welcome you on behalf of the Faculty of Natural Science at Stockholm University, which hosts this climate lecture. This is called the Bert Bolin Climate Lecture, and a lot of you may know who Bert Bolin is, but I'll just give you a little introduction. Bert was a professor here at Stockholm University in meteorology. He worked quite a bit in weather prediction and then got into the carbon cycle when this was new, understanding how carbon moves in the environment. And he began also to be more and more involved in work with climate and how carbon affects the climate, carbon dioxide. And through his career, he sat on many different organizations, in many of them chairing these organizations, working with these issues and understanding how climate and other parts of the the Earth system are connected. And in 1988, he was asked to be the new chair, or the chair of the new Intergovernmental Panel on Climate Change. And he led IPCC through a number of their scientific assessments, which have been given out regularly over the years. And these are the reports that are used nowadays to essentially try to chart out how the climate is changing, the scientific basis, but also understanding how this is happening and why it is happening. And it has become more and more evident over the years that this is due to anthropogenic influence. It's our use of fossil fuels and burning oil and coal and releasing large amounts of carbon dioxide and methane into the atmosphere. So Bert Bolin was a very influential person in climate change research. And when we formed a climate research center at the university here, it was only natural that we decided to name it after Bert Bolin. So this is why this is the Bert Bolin Climate Lecture. So I'm going to leave over to our scientific director at the Bolin Center to introduce the speaker for this year, the 2017 Bert Bolin Climate Lecture.
Thank you, Cindy. So, my name is Nina Kirchner. I am an associate professor of glaciology here at Stockholm University, and I'm also the scientific director of the Bolin Center for Climate Research. And it's my pleasure to introduce today's speaker, which is Tom Cronin. Now, this is not a totally easy task, because usually when you introduce a speaker, you go briefly through his CV. But Tom's CV has 26 pages when I try to write it out, so I will not go through everything. But Tom is a senior geologist at the US Geological Survey. He is also adjunct faculty at Georgetown University, Walsh School of Foreign Services. And Tom has had a long career. He's an outstanding scientist. He has been working at the Office of Science and Technology Policy to the White House. And he has done a lot. Whenever I have a question I feel like I have no clue about the answer, I feel like I can go to Tom and he knows the answer. Tom is also excellent in communicating what he does. He has experience with media and everything, and I'm sure that he will be a great lecturer. You will give a fantastic lecture. You are welcome to raise questions, ask questions while Tom goes, because we want you to really go along with him. Tom can be provocative, he can be very entertaining. We want you to have fun. This is going to be a lecture that is for you. And with that, I think Tom would like to welcome you up here so that we can enjoy this year's Bolin Climate Lecture.
Thank you.
You're welcome.
Thank you, Cindy, and thank you, Nina. It's very nice to be back. I have a lot of close colleagues and friends here. I've admired their work, and the Bolin Science Center. It's a valuable resource that you are lucky to have in this country and in this city. Don't ever forget that, because these issues are of significance to everyone on the planet, not just here in Sweden. And do interrupt me. You can raise your hand. I might not see you. The lights are bright. But if you don't understand, and I know I'm speaking to a diverse audience, and some people who aren't quite yet trained in the sciences, and some of the stuff I'll talk about is difficult. I don't care, okay? It's difficult. I can't make it simple. That's the problem with the whole issue of climate change today, is people dumb it down and try to make it too simple. And it's not. Now, the most important thing about this lecture, this discussion, is the person who we're honoring here, Bert Bolin, who I may have actually met in the 70s, and there may be a faculty here who remember him and certainly know his record better than I do. But I'm going to try to tie him into the lecture and what he contributed, things that are almost unbelievable for his time. and I'm going to start with that now. And it has to do, of course, with climate change in general and specifically carbon dioxide in the atmosphere. That's too busy. But you know what it says? It says what Bolin said with Ericsson in 1959. I was just a little kid then. And there it is. Changes, which is the, there it is. That's the, see the little red dot? Okay. Changes in carbon dioxide content of the atmosphere and sea due to fossil fuel consumption. It's of some interest, so understated, it's of some interest what they might imply with regard to future climate change and CO2 the atmosphere, okay? And this is actually the curve, and you all have math, showing the year 1900 and the year 2000, we're about here now, and the rise in carbon dioxide for the future with an error bar. And he did these calculations and made the very modest statement, the implications with regard to the radiational equilibrium, that means temperature, energy, in this case may be considerable, but falls outside the scope of this paper. He made predictions, and guess what? His predictions calculated on the back of an envelope, I said, here's what he said. Number one, he concluded there is an appreciable rise in CO2 in 1959. We had no CO2 curve from any monitoring station. And number two, he actually predicted in the year 2000 roughly a value that we get actually towards the higher end. That's kind of amazing that he said this then. The climate issue is not new, and Bolin anticipated this with very modest statements. There is 1960 is right here. 59, that paper was published, and then they established the Mauna Loa, Hawaii CO2 curve, which is so famous, I'm sure you may have even seen it. There's the methane curve here and the nitrous oxide curve, other greenhouse gases. So he predicted that, and there it went, and it went right up to where it is today. He was right. His paper in 1959 was quantitative. He had 48 equations. That's too much for me. And big equations, too. He was a meteorologist, multidisciplinary, had oceanography, biology. He basically predicted the Mauna Loa CO2 curve, or actually recommended it, that we just saw. This was before any of the ice cores in Antarctica were taken of any significance, which have the trapped air bubbles and the CO2. It was predictive. As I just showed you, he predicted the concentration, and it was very, very understated in terms of its conclusion. The implications with regard to the equilibrium of the Earth may be considerable. You don't see a lot of papers nowadays that have so much in so little, that are so important, and so little arm waving. So I want to give a tribute, a shout out to Bert. That's much too complicated for people with your background. That's right. It's exactly what Cindy said he became an expert in, and that's the carbon cycle. It's not that complicated, though. There's the ocean and the land and the atmosphere. And in this diagram, you can see how much carbon is in each of the reservoirs and how much it's changing on a yearly basis between each reservoir. He wrote papers on the ocean reservoir, for example. In 1977, he wrote a paper in Science on the terrestrial biosphere. And in red, which you can't read these, doesn't matter, this is the flux in carbon dioxide related to human activity. He anticipated all this. This is, as Cindy said, the IPCC, Intergovernmental Panel on Climate Change, their latest report, 2013. Bolin was the boss of the first one. And so you can in some ways see this as his and many other scientists' legacy. Okay. You have to remember three little things of 3 letters each. okay? If you can remember those, especially this first one, then you're a winner, you understood me, and I'm successful. Okay, so remember that. In the future, I'm going to talk about OAEs here, GICs, AGW, and if I have time, EEC. The first one's my favorite. Oceanic Anoxic events. Does anybody know what an oceanic anoxic event is? Good. If you can get this one, then you understand the problems of modern climate change. I'm a geologist, okay? So bear with me. What I won't get into are the things you hear about in the news, maybe in your teachers. Some people might say, this is the face of climate change, right? What do I mean by that? Come on, someone answer me. What do I mean by that? Somebody in the front row, go ahead, don't be afraid. Why am I showing a polar bear? Come on, you live up here in the north. Melting sea ice, their habitat. Right. Does anybody think the polar bears are threatened? Good. This is one view, and I call it a popular view. There's another view. My point is there are different ways to view the data, which I happen to know. This is Martin Jacobson. He's right here. He took this beautiful picture as to whether or not they're threatened. And that's as far as I'll go in terms of what is the face of climate change, as you'll see by the end of the talk. And the two themes I'm throwing out here, in addition to building on Bolin's work, are the climate change records of the past in the geologic record. Number one, and I think I have a little bit of leaning towards the high latitudes where I've worked on and off for a number of years. And that's why I throw this in here, because that bear is eating on sea ice, and that's one of the other symbols of concerns about climate change. I'm a geologist. I'm not a climate modeler. I don't predict the future, but many, many people do, really smart people. I mean, you know, they predict the future. Problem is they've been wrong. Wrong about the temperature rise, wrong about the rate of sea level rise, wrong about the rate of sea ice decline. The sea ice here in the Arctic is shown going back to 1900, right here, and this bunch of wiggly lines with the black, the mean average condition in the middle, are what all the models said. The problem is that what the sea ice actually did was decline faster. And this is not the only part of the climate system that the rate of change was underestimated. That's kind of scary. It means we have to improve the models. This is a map on the left of the same thing, only showing the North Pole. Where are we? Over here, North Pole, Alaska, Canada, Siberia, and the red means the sea ice is declining in these margins of the Arctic. If anybody ever says to you, the polar ice caps are melting, please correct them. What is a polar ice cap? I don't know. This is sea ice. These aren't glaciers. And it's decreasing during the summer months in these parts of the Arctic. Correlated with that are increases in the biological, remember the theme of the talk, all of these things have something to do with biological processes, is the productivity. This is basically showing you the same thing that red line said in the last talk, and that is things are changing very quickly. And what I do, okay, so this is what I do and many of my colleagues. We study climate changes of the past. We use ice, that's a glacier in the Andes, but more often the important records come from Greenland and or Antarctica. Those are ice sheets. This is a glacier, not sea ice. Here is sediment. Anybody who doesn't think those different sedimentary layers are cyclical, come talk to me afterwards, because they are. They're beautiful. That's in Spain. You don't have this kind of geology here. Some people go underwater and core coral reefs. I don't. And some people look at tree rings. I don't. But my friends do. And these are just some of the archives that capture climate changes of the past through different measurements, physical, chemical, biological, captured in them, okay? Paleoclimatology, and those are... Now, this one is really simple and important for you to understand the climate changes of the past and their relationship to changes in atmospheric carbon dioxide. Wouldn't it be nice if we knew that relationship? Because nobody knows what's going to happen in the future, including the actual level of CO2 that we're going to stabilize at. On the left is less CO2, and those are ice ages. That's radiative forcing, which simply means how much heat and energy there is. You get an ice age when you don't have a lot, at least in the right places on the planet. And these are warm periods with high radiative forcing. And the red and the blue are showing you warming during interglacials and blue ice ages. Warmer, cooler. This is the relationship in one slide of carbon dioxide concentrations in the atmosphere of the Earth to ice ages, and what we're especially interested in, the opposite, hyperthermal, very warm periods of climate shown here. So I'm going to show you some stuff from the Cretaceous. Now you know about the Cretaceous, right? Who lived then? Good. I'm going to go back to the Cretaceous in a second. Really warm, high CO2 concentrations, and we experienced on this planet ocean anoxic events. So we want to look at these in detail, and you'll know why by the time I finish this part of the talk. Okay? CO2 and temperature are highly correlated on the planet over millions and tens of thousands of years. I love this slide. I love the background, okay? If you remember the three letters and what I explained to you now, you're going to understand the whole climate change problem. I don't care who you are. They were defined in 1976, seminal paper, great to read. But the world was different 93 million years ago and 120 million years ago. What was different about it? The location, position of the oceans and the continents because of what? Seafloor spreading, plate tectonics. We didn't always have the same configuration. And what you see here, there's North America. If you ever go out to the western United States, you know that it was flooded during parts of the Cretaceous. Here are the ridges that are spreading in blue and red. And here's the Middle East during the Cretaceous. I put a big star there. And there's a star at Italy, because I'm going to show you pictures from Italy, and I'm going to show you the hard physical evidence for climate change and global warming. Let's move on. So you see the Earth as it existed. By the way, this ocean was called Tethys, had its own name. And what this plot shows is petroleum source rock, marine extinctions, sea level, temperature, and atmospheric CO2 between 0 and 600 million years ago. Wow, I didn't know we knew all that. Well, we do. Petroleum source rock, what does that have to do with this talk? It has to do with the explicit link between climate and energy, and where that energy is in terms of petroleum. This topic has been studied in detail, and let me add, the biological extinctions are huge. You can see them being semi-periodic and occurring during these climatic excursions called oceanic anoxic events. So we're linking it all here. The CO2, the extinctions, the world's ocean becoming anoxic, no oxygen, I'll show you in a second, and the climate driven by CO2. There's an OAE, See how I did that arrow? I did that myself. I didn't have to ask any young person. All right, next. That one's 93 million years ago. That one is right here. Right here. Okay? The Earth warmed by 4 to 8 degrees. It's called the Rayleigh event. I'm going to show you a picture of it. Anybody can see it. The next one here is 120 million years ago. 4 to 8 degrees warming, two-step doubling of CO2. Where's the CO2 coming from? Probably volcanic activity. If you go anywhere in the world, you're going to find evidence for it. Not just in the ocean, you're going to find it in the basalts, lavas, that are all around the world. Write this down. This is your homework assignment. Find a map of global large igneous provinces, lips, and you'll see what I mean. Lots of volcanic activity. And not only does lava come out of volcanoes, but so does CO2. Not complicated, very simple. Those are the two events I'm going to show you pictures of. I did that too by myself. Okay, so let's go to the next one. And there it is. You go to Italy, nice place, very nice place, and you can see the rocks. And you can see these dark layers in here. They are black shales. What is a shale? Come on, help me. Loud. It's a rock. That's not hard. It's a rock. And they're black because many of them have organic material in them. And in Italy, some of the most famous have been studied to death, including that one, which is an OAE and is the younger one, I think. No, that's the Albion-Aptian, which is 120 million years old. And now I'm getting closer to it, and you can see it's really clear here, but below it, which is, of course, is older, stratigraphically, and this is younger, you have all these layers. Limestone, marl, which is kind of a sediment with calcareous material, back and forth. Those are cycles. But within the cycles, you see this black shale. They're global. The whole ocean, for all practical purposes, went anoxic at this time, due to the reasons I just explained. There's the 93 million year one, right up in there. And of course, you see cycles here and here and here. That's called the Cenomanian Turonian. The dinosaurs were still around during all these things, but they were on land. This is the ocean, the global ocean, oceanic and anoxic events. And what happened during these is that. And this is easier than the other one. Look, CO2 coming from the land up here, greenhouse warming, carbon dioxide being taken up by the ocean, gas hydrates and organic material accumulating in the sediment. See the bone? That means it's a fossil in a laminated black shale. Okay? This is the early phase of the OAE. Jenkins wrote a beautiful review article, but it's not hard to understand. You probably know more chemistry than I do, okay? This is the late phase where the oceans become kind of ugly. Cyanobacteria, deposition of organic matter, and all this is just more technical stuff. But the fact is that the outcome is a really miserable ocean with low oxygen and no recycling of the carbon, and those black shales accumulate 10 to 15% organic carbon, and they become the source rocks for geologists and geophysicists to go find oil and gas. All because of a period of global warming, globally, called an OAE. And all of these processes have a lot of biological processes involved. The drawdown of CO2, for example, might be the biological pump, biological activity. But it's not a good place to live. Those cycles, I deliberately put this, I say don't show them that, it's too complicated. No, it's not. It's those cycles. Cycles driven by the orbit of the Earth, which I will get into in a second, shown here. And basically, organic, rich, marl, limestone. The end members of those different kinds of rocks, the lithologies, are controlled by climatic cycles here, and the obliquity, that's the tilt of the Earth, and during different levels of eccentricity and the orbital shape around the sun of the Earth, circular, elliptical, and the wobble. You put all those together and you get those cycles 93 million years ago. And those cycles are, by the way, what I'm going to talk about next, and those are our ice ages for much more recent time. Okay? So in summary for the OAEs, this is what happened on the Earth. Periods of global warmth, high atmospheric CO2, anoxic acidic oceans, high sea level, major extinctions, black shale, major petroleum. This is what's happening today. Warming climate, rising CO2, ocean acidification, melting glaciers, rising sea level, biological response, ecosystem stress. Gee, those are almost the same. Next. GICs. I show this slide again. These are orbital cycles. Let me use the term orbital or astronomical cycles to refer to these category of climate change and variability. They're critical. They are basically the explanation of the ice ages that we've had in the last million years. They're the pacemaker of the ice ages. You were covered with an ice sheet here not long ago. And so we're going to look at these cycles briefly. I don't want to go over my time, but I'm doing well, right, Nina? Yeah, I got a lot of time. Okay. Those are cyclic. They're not the same ones I just showed you in Italy, but they're driven by the same processes. And here's a beautiful recent slide by Dave Hodel at Cambridge, who's one of the leaders in this field, celebrating a paper written 40 years ago on the pacemaker of the ice ages. Again, the shape of the Earth's orbit, the tilt, which goes from 22.5 to 24.5 degrees, roughly, which changes the seasonality, you know that, and the precession, the wobble. And you put them into the mix, and what does that mean, the climate system? That means the sea ice. That means the carbon dioxide. That means the terrestrial biosphere. That means the ocean circulation, which takes time when you get deep ocean circulation. It means all the other components of the climate system are basically catalyzed into reacting, but they do so over different time scales. But they're the pacemaker, like a heart pacemaker. And then what you get out are ice sheets right here. This is the polar view. There's Greenland. Here we are over here. Here's Siberia. And there's the interglacial. Those are two extremes you have to understand, because this interglacial condition is your pre-industrial condition. Excuse me. So investigating these processes are essential. Okay. We love wiggly lines in our business. I'm sorry, but you have to deal with them. And here is a wiggly line that goes back 600,000 years. Try hard. Most people aren't used to dealing with different timescales, or timescales like, it's kind of like the deficit, like the budget deficit. Once they get to the trillions, you know, we tune out. We have no clue what that means. When I get to the millions of years, don't tune out. You have to tune in to the different timescales, because you're still young. You're going to live a long time in terms of geological time compared to me, and so you have to pay attention to this. The oxygen isotope ratio here is a standard measurement of protists that grow shells in the deep ocean, and that we measure the ratio of the O18, the heavy, to the O16. I'll tell you why. Because that's influenced by temperature and the size of the ice sheets. Because the ice sheets preferentially take up the light isotope. There's deuterium. What's deuterium, you chemistry people? Heavy. Thank you. Good. And there's the CO2 from 3 different ice cores. The magic numbers here that you must remember, and if any of your teachers are here, I want a quiz on this, are 4 numbers. The pre-industrial concentration, can you read that? 280. That occurred 125 years ago, 125,000 years ago, 200,000, 300,000, 400,000. That's the CO2 concentration. What was CO2 concentration during ice ages? 190 to 200. This is natural. And the primary reason that the CO2 in the atmosphere was lower was because the oceans took it up. It's a totally different time scale from the ocean anoxic events. The 2 numbers, 280, 200, 190. What's the 3rd number? Today's concentration. What is it? Thank you. Just a year and a half ago or so, it hit 400. 400. That's natural. 400's not natural. What's the 4th number? I don't know. That's the number that people want to know. Where is it going to stabilize at? All right? And that could be 600 parts per million. Now, I showed you a curve before that showed by the way, this is really good data because this comes from the bubbles in Antarctic ice. The older, and it goes back 800,000, the older estimates are not quite as firm because they are not from ice. They are from other methods to reconstruct CO2 concentrations. You want a good thesis to become famous and a famous professor and make a lot of money, then figure out other methods to reconstruct CO2 in the past. But here we have the last 600,000 years, the last 7 or 8 glacial cycles. And these are same things reflected in those rock records. Let's go to this last interglacial here, which is very important here, 125,000 years ago. Anybody go to Florida? Anybody been in Florida? I don't like it either, frankly, but the geology is really good for this kind of stuff. And there's Key Largo limestone. It's a limestone. It's a coral reef rock. You know what that is. Not here, but you've traveled. You've read. And it's about 5 or 6 meters above sea level, and it means that sea level was higher during that last interglacial than it was in the last 10,000 years. We don't know why. But it's a reflection of the subtlety of these warm periods in the past being slightly different for reasons we don't know why. And it's not CO2, because the CO2 is the same as pre-industrial. It's reflecting the glacial and interglacial cycles with a twist in that they're not all the same. In the Arctic, it's easy to see the orbital cycles if you go out to the Arctic on your ship, the Odin, or another ship, and take a sediment core. You can see these cores. Just go over to the geoscience building and ask one of my friends, tell them I sent you, and maybe they'll let you see the mud, because the mud represents dark layers, interglacials, gray layers, glacials. These white layers are ice-rafted material from gigantic icebergs coming off North America. They're Paleozoic dolomite. And we have different age markers. The point is, not only is the reef record of Florida reflecting these cycles, but the mud in the Arctic Ocean, and so are the animals that live in the Arctic. At the surface, this planktic foram. At the bottom, this benthic foram. At the bottom, this ostracod. And there are others. Okay, so has this topic been of interest to anybody? What do you say? I don't care about this. He's the only guy who does this. No. It's so important as a reference point for your future climate that all of these locations in the world's ocean represent someone going on a ship and taking sediment cores and doing just what I just did with many methods for that Arctic core. So if you don't think we know about the world in the past, we do. 125,000 year ago reconstruction showing you by color here where it was warmer, where it might have been a little cooler, a global temperature map. And to go with that, that's real data from mud. To go with that real data are climate model simulations that try to confirm or refute, and you can improve the models by looking at the real data. This is a big enterprise in our field, but don't let anyone tell you that we don't have a lot of information. Let's go to the opposite extreme. The last ice age. We call it the last glacial maximum. 20,000 years ago, green, and if you like biology, foraminifera, triangles, dinoflagellates, diatoms, radiolaria, different geochemical methods, okay? And you can see the different method and the distribution of glacial sites in the oceans. Forget the land, we have a lot of those too. So we know a lot about the last ice age. What was the CO2 concentration then? Good, excellent. That's good. Gold star for that guy back there, okay? I'm very generous when people know the answers. So you have the two levels. You have the interglacial at 280 and this. The world was very different, and these are not long time scales. Some of these events, the transition during a cold period, an ice age, and an interglacial are relatively rapid. Let's go. This one's the LGM, again, by Kucera and his colleagues, showing you the world's ocean and cooling, -10 to -5 degrees. In brief, here's a good number for you. During the ice age, the global climate changed about 5 degrees. You could do it on the back of the envelope. 5 degrees and about 80 parts per million volume. That's that slide I showed you earlier on the climate sensitivity to changes in CO2, reconstructed from hyperthermal periods and ice ages in the past. We can do this. And I don't want to get into this discussion of what is a safe, acceptable level of CO2 concentrations in the world today. Obviously, that's a hard and subjective thing. But many people tie it to the sensitivity of the Earth to CO2. And we should, for example, you've heard it, 2 degrees warming. Can't go past that. Dangerous to humanity, okay? You can take all this data and more and actually evaluate that, especially if you add the climate models. That's what people do. What's the safe, acceptable level? I don't know. That's a subjective. I'm just a scientist. I don't deal with that. I deal with trying to do this stuff. But remember, 5 degrees warming for an ice age, and how many degrees did I show you earlier during, for example, the OAEs? 4 to 8 degrees. And we know that paleo CO2 concentrations, not nearly as well, but we do know them. Let's talk about that polar bear again, can we? Not a lot of data on that animal, okay? Probably evolved 500,000 to 1 million years ago based on molecular phylogeny and DNA biology. But let's talk about an Arctic animal that we know a lot better. At a little forum I showed you the electron microscope picture of. This is the North Atlantic, okay? Today, 18,000, 21,000 years ago. This is the North Atlantic. Where are we? Over here, okay? Red, blue, green are all color-coded. And what this basically shows is during the ice age, let's stick to this one, compared to today, this coal-loving animal, we know a lot about it, genetics, everything. It's all over the Arctic. It's one of the most reliable indicators of cold surface ocean. Came south. Of course, if you talk to your own Swedish scientists over here in the other building, you'll see that that's partially because the Arctic was covered by a gigantic ice shelf. They just came south, and they did this over and over again, okay? Who do you think came south with them? Sea ice. What else? Seals? Absolutely. Bears? In fact, Professor, if what you're telling me is true, you should be saying this, then, and most of the time we were really in a glacial or near a glacial, then wouldn't that mean that the polar bears and their associated ecosystems actually lived outside the Arctic more than they lived in the Arctic? I didn't say it. You said it. One could easily argue that they were doing the same thing as Pachyderma, the little protist forum. All right, let's go on. Let's see what I have next. Oh, yeah, it's the last one. Oh, this is a good one. This is used a lot. I don't know why they thought anthropogenic global warming. I'm not going to talk about global warming, okay, except a little bit. And I'm going to do this because I'm in Sweden. You see the bottom? That's the basic issue that many people are addressing, distinguishing natural versus human-induced climate change. Anybody heard of the hockey stick climate curves? A few? Well, you're going to learn about them. You ought to know about them. There they are. I thought this would be easy. Of all the places in the world, I can only think of 6 countries who actually know what a hockey stick is. Czech, Russia, Canada, US, Finland, and Sweden. No, they don't produce many good hockey. Okay, we're in the Stanley Cup playoffs here. We're talking about serious stuff. And the hockey stick curve is described as such because there's the part you hold and there's where you hit the puck with. This isn't a field hockey stick. But if I gave this talk in Cuba, I don't know about hockey sticks. Call it a baseball bat, but it's not curved. So it's a bad name, bad name. But I like it here because it's so prominent in the last 15 to 20 years of climate studies. And there it is. What is it? It's easy. Instrumental records, thermometers, satellites, tree ring records, and a few ice core records and corals here. Going back 1,000 years, other curves go back 2,000. And that is the temperature anomaly, meaning depending on what mean condition you take. Bottom line is there's fluctuations during the medieval climate anomaly. That's your little ice age, and that's your global warming. The empirical temperature reconstructions by many authors, which are not all listed here. What's that? Volcanic forcing. What's that? Solar forcing. Not the tilt and all that stuff. This is pure changes in the sunlight coming out of the sun or reaching the sun. And that's so volcanic activity, because big stratospheric low-latitude volcano eruptions usually cause cooling globally for a couple of years. That's why these point down, solar up and down. And there's your greenhouse gas forcing in the terminology of other forcings, and there it is. So the upshot of the hockey stick curve study, based on the experts, and there are many, is that this warming is primarily can be explained to a large degree by the greenhouse gas forcing of the last century. And this natural variability is hugely important, and there is some influence of these factors. And in my opinion, we need a lot more work on this. So that's your anthropogenic warming curve. And if you don't think there's good data for that, then read all these papers here and those that have come out since 2013. The farther back you go, that's 1750. That's because there are a lot of trees around that you can do tree ring studies on. Fewer trees, 1,500, 1,000. Okay, there's a lot of data, all paleoclimate data. Here's the Arctic, because we're here in Sweden, and some of the sites that have been studied using different techniques. And what does that produce? A composite. And by the way, that last curve was most likely northern hemisphere temperature. Southern hemisphere is not as well covered. And there's your hockey stick curve for the Arctic. And the lower panel is the best one. Temperature anomaly, back 2,000 years. There's your little ice age, and there's your warming. That's what the data say. Okay? So that's the third topic. And EEC. See, I'm old. These things don't matter to me. But they matter to these people. They're my girls and boys. They're mine, or my sons, but they give them to me every weekend. because they're going to matter, because everybody's living old now. Who knows what they're going to see, but they're going to see changes in the CO2 concentration and perhaps a plateauing. Okay, for you future scientists, we're going to lighten up here in terms of the technical aspect of this talk, because I have the recipe for you to get a good PhD, get a job, become famous, and that is to publish in the leading journals, right? Anybody can do it. Nina can do it if she writes a paper using my method. It's not my method. It's not my method, but it's the truth. And it's biological, which is, we're coming around to that link. Remember the question in this talk, what would Bert Bolin think, given what he did in his career and in that 1959 paper? So let's take a quick look. I'm going to go through these fast. You can ask me afterwards, all right? There's your Cenozoic curve after the, for temperature, carbon dioxide. I told you I like wiggly lines. So let's just get some context here. 60 million years. There are your CO2 concentrations. There's pre-industrial. So there's 1,000. That's not hard. Remember? I told you 4 numbers. 200, 280, 400 today. Future. Well, we can add a 5th. Go back in time, and during the global warmth of the Eocene hyperthermal climate, might have been 1,000. Okay, and there's your temperature curve, major glaciations coming up here, and all this other stuff. And there's global sea level falling, 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 and then oscillating. We talked about sea level at 10 o'clock in the lecture. And there's the secret. What do you see? Yell it out. You know, if you were my class, I'd know all your names by now, and I'd just pick you out. I'd make you come up here. I'd make you go up to that screen and say, where's the porpoise? What do you see? Come on, you can't be wrong. I'm not grading you. Look, what do you see? Little animals, little silhouettes. Look where it's published. The I'm a fellow of this organization. I don't even know what that means. American Association for the Advancement of Science. Science and Nature, everyone knows, are the leading journals for impact, promotions, getting grants. And these guys got a paper in there, and there's a very prominent scientist by putting little silhouettes. How about this one? It's a genetic study by a German scientist named Frank Haller, excellent study, showing you the divergence of the polar bear from the other bears. And needless to say, it does correspond to some of those climatic events I talked about very briefly. But the secret to this paper isn't the oxygen isotope curve or the genetics or this cladogram. It's those. And they're not even silhouettes, so this is better than most. Here's one. Oh, my God. Cooper et al., looking at the last this is 4,000 years ago. So this is, you know, these are mastodon. You've heard of the Pleistocene extinctions, right? Saber-toothed tigers, mastodon. Where'd they go? Well, it wasn't that long ago that they were here. These people tried to take the Greenland ice cores records shown here. Come on, baby, I can do this. There you go. Right down here. Again, oxygen isotope curves and the Cariaco Basin sediment record. These are abrupt climate events, 28,000, 36,000, 40,000, and link the timing through vertebrate paleontology. There's the great Irish elk. You've heard of that. You've probably seen it in the museum. All these. This is a fantastic study. But why do they get published in Science? Come on. Silhouettes. It's a great study, seriously. I don't believe that they have enough data to actually make this, but what they're doing is linking the biological systems to abrupt climate changes, which are recognized really well. It's a really good study. Climate-driven changes in the distribution of life on Earth are affecting ecosystem health, human well-being, and the dynamics, challenging local and regional systems of governance. Whew. Silhouettes, science, okay? There's a little bug up there, see? Everything's our governance. Governance. Biological, okay, so, well, am I missing the one that had the little, no, there it is, see? The coffee bean. What could be more important? I'm worried about climate change and the coffee bean. And this silhouette paper showed me. So I'm going to conclude here by asking a hypothetical question based on what I just showed you in terms of paleoclimate reconstructions, past climate biological links from fossil records and climate curves, and future projections in that last slide on what agriculture and other human-related ecosystems are going to do, and ask the question, going back to what Bolin began his career as a meteorologist, mathematician, shifting into climate models, carbon models, and then becoming an influential policymaker. What would he think of some of these biological studies and the quantitative link of climate and biological systems? Anybody want to answer that? That's all. That's all I wanted to say. It's not simple. Don't believe anyone you read or hear or blog. Find out for yourself from the scientific literature about all of these things, and take advantage of the experts you have right here across the path. Thank you. Oh yeah, this one. Thank you, thank you. Thank you, Nina, and Matt, and Martin, and Jan, and Karina, and Cindy, and a lot of my friends for this. There's your ship, by the way. That's yours. Thank you.
Thank you very much,
I'll take any questions. You didn't talk enough. You didn't ask me enough questions. There's no bad question. So go ahead.
Yes, we can do it like this. Obviously, you are not scared to death yet, so that is perfect.
That's good.
And we will accept, I just say this now, you have to deal with it. Tom will accept any question. It does not have to be related to the talk that he's just given, okay? So please feel free to ask any question you'd like to ask, and Tom will be happy to answer. And I think we have Lina going around with a microphone so that we can hear, because it's a bit difficult if we don't use it. So who wants to be, if you're not first, we have people here who pretend to be the first if you don't dare. But please feel free to be the first one to ask a question. And we can go down if that makes it more familiar.
I can just point to one and say...
I know you can do, but...
And if you don't ask me a question, I'll ask you a question.
Now you give them a chance to... They start, okay? So, who wants to ask a question?
Oh, man.
The lecture
you want the slides off or copies? The technical people have streaming and recording.
Yes.
Send me an email. I'll send you what you want, so long as it's not copyrighted. Everything here is published. Many of them you can actually get in 2 seconds at a website. But I'll be happy to just send me an email. I'm available.
This lecture is recorded. It can be watched from the Bolin Center's homepage. If you go into bolin.su.se, you will find a link, and you can watch it, and you can share it. So, there's a question.
Go ahead.
And tell us who you are. Makes it more fun.
All right, I'm Steve Lade from the Stockholm Resilience Centre at Stockholm University. You've talked a bit at the end here about how climate affects biology,
yes,
and silhouettes as well. What, in your opinion, is, on the timescales you've been talking about, some of the most important ways that biology affects climate?
That's a great point, and I should have been more explicit when I covered, let's say, the biological pump, because that drawdown of CO2 into the world's ocean during the glacials, to me, and maybe they don't use the same term, but it's the holy grail, because the oceans, partially through the solubility aspect that Bolin worked on, but also partially through the biological pump, which simply means that the biological activity at the surface of the ocean, especially in areas that are low concentrations of high nutrient, low chlorophyll today, are one idea is utilizing nutrients better, and therefore it's that biological system, photosynthesis, and then the whole food chain, that's taking up the CO2 from the atmosphere and storing it in the ocean. And of course, then when you end an ice age during a glacial, you send it back to the atmosphere. And so you're seeing a huge transition of the carbon system. And if we could understand that as kind of a holy grail of the carbon cycle, that's biology, okay? Pure and simple. Obviously, it has to do with ocean biogeochemistry. So biology matters there. I would never want to shortchange the terrestrial biosphere either, which Bolin wrote in his 1977 paper in Science. It's a beautiful paper because he really brings land use change into the equation. So biological systems on land and how humans have used them, and naturally, are other factors, especially in a subject I didn't talk about, and that would be methane, because that's the exchange, the terrestrial biosphere to the atmosphere that's most important for methane. In terms of, you could view some of those major transitions in the Cenozoic record from an evolutionary standpoint and view the response of the biosphere through extinction. Of course, then also speciation and radiation. You could also, if you took the much longer view, look at the evolution of land plants and certain organisms that do photosynthesize in terms of the long-term, and by that I mean hundreds of millions of years, the long-term evolution of the Earth's atmosphere. So it's relevant on different time scales, but it's certainly relevant. Biology plays a huge role. And some of these studies modeling biological response into the future, I think have that in the back of their mind, but it's much more trying to take the climate models predicting future climate and seeing what they might do to ecosystems. Some are also just monitoring instrumental records. What are instrumental records showing in terms of biological systems, ecosystems, both at species level, ecosystem level? And there's one more thing that's really important, and that's the whole issue of detecting and attributing trends and patterns to climate change, either natural or anthropogenic, detection and attribution. And there's a really wonderful term going around now that I've just watched. And we always hear about temperature and the temperature plateau, and why isn't the temperature doing this and the temperature doing that? But there's some really good studies on what people call the time of emergence. When should we see an emergence of a particular part of the system from the natural climate variability? A beautiful paper by someone named Keller, 2014, dealing with the sea surface temperature and other aspects of the ocean. And in fact, we should be seeing acidification emerging as anomalous long before we see sea surface temperature emerging. We should be seeing dissolved inorganic carbon, all these biologically related in terms of biogeochemical processes. So I guess, you could say it depends on how you define biology, but all those factors, all time scales, there are a few examples. Another one. Sorry for the long answer.
I'm Gunnar Tersian. I work at the Analytical Chemistry Department. These ocean anoxic events, I guess they're linked to extinctions in the ocean. Is that true?
There are extinctions depending on which groups, yes, yes.
But how do we know anything about what happens to the terrestrial life during these warming events?
Yes. Fossil record, I don't know the actual literature on terrestrial, either paleobotanical or vertebrate paleontology. I would speculate it's much less significant. If I took the example of the PETM at 55, 56 million, it was like an incipient OAE, and it's recognized in the terrestrial systems in the Western North America, elsewhere. I don't think there were major extinctions during that very brief 200,000-300,000 year event. So I don't know. I can find out, though, for the OAEs about the terrestrial systems. I don't know of literature saying there were large extinctions. Excuse me.
Yes. Yes, hello. My name is Simon Larson. I'm a PhD student here at the Department of Physical Geography. I'd like to thank you for this great lecture, and a lot of the research that you presented here and the results therein, I think we all here agree are we can at least interpret as evidence for what we know about the climate system. But there are a lot of people all over the world who, for some reason or another, don't believe in what we are discussing here, that people, mankind, and our actions are actually what is producing the climate changes that we can observe today, and that these are possibly not natural. So I was wondering, what was your take on that issue? How do we reach out to society and people with these kind of results?
Is the recorder off? No. I just want to get back in. I live in Washington, by the way, okay? Of course, that's the $64 question, and I'm just, seriously, I'm just a scientist. I know scientists like me who are strong advocates of action, but you're not really talking about action. You're talking about educating, excuse me, and informing. And in my opinion, we talked about this last night.
Yeah, we had a panel discussion on that.
We had a panel discussion, and I think the professional societies have to play a larger role. Excuse me. Individuals show their opinions really well, too much. Blogs. And it depends on which people you mean you're trying to reach. Politicians, developing countries. The media is not going to do it, okay? In my opinion. I don't think, as we discussed last night, there are enough qualified scientific journalists. I think that there are a lot of journalists that want headlines and want scientists to arm wave. I don't arm wave. Other people do. They want it. They want the soundbite, 24 news cycle. My most reliable source, I think, would be the major Ecological Society of America, American Geophysical Union, American Meteorological Society, equivalent organizations over here, where they have policy statements and reviews and discussions. And I guarantee you, if you went to a large meeting of the major societies, you would find sessions on communicating science. You'll find research scientists, research people at universities doing research on this very topic. You know, I'm sure, with that question, the history of this issue. It's not new. It goes back decades. Bolin was at the forefront in starting it. It went through the Kyoto Treaty in Japan in '97, Copenhagen, 2009. Now you got to Paris. So, in short, I don't know how, except education through various parts of the system, and that could come from teachers themselves, but it also comes, the best sources, objective, clear-cut. All right, so I saw these people being interviewed in the United States. One guy was called the science guy. One guy was a very famous professor. You see him all the time. You'd know him. I'm not going to mention names. And then another guy is very famous. None of them do what I'm talking about here, or what my colleagues. And I saw him in the last 2 weeks on TV. What is coal? It's coal. Everybody knows what coal is, like forest. Died hundreds of millions of years ago and left this stuff. Would that be right? Not all coal formed back there with the giant dragonflies. Don't say that if you don't know what you're talking about. So I hear people who are purported to be the spokespeople, the ones who can do this communication, all right? In theory. They're always guests. And they're almost always wrong. So I don't trust them. Do you trust blogs? Anybody here blog? Yeah, it's fun, you know. Anybody can write anything they want. Isn't that great? Nobody slaps you on the wrist. You never get penalized. You don't lose your job. You're going to believe them? Believe me. Next question.
Is there more questions here? Where's the microphone? Yeah, okay, go.
All right. Hi, my name is John. I'm doing my hydrology master here at Stockholm University. And I remember a lecture a few years back. One of my lectures talked about quantifying like carbon storage in permafrost. And I remember also the person said that like this has not really yet been incorporated into the climate models. And I was wondering what your take is on that, and if you know sort of where we're at right now.
I'll tell you where we're at. Number one, I'm an ocean guy, so I'm not strong on that. But number two, I know a lot of people who work in permafrost and carbon cycling in the Arctic. In fact, the scientist right in the room next to me where I work, and I know there's a lot of others. I also have good friends who do the methane in the submarine permafrost from that standpoint. And if you're talking about the uptake of carbon during ice ages, that's a very interesting point. And there have been people who have promoted the ocean as less important than we thought. But in terms of the release of carbon, we had massive releases of methane and terrestrial carbon during the termination of the last ice age. Really nice paper by McDonald. It's a little out of date, showing that 14,500 years ago. There are people working all over the Arctic, Canada, Alaska, and Siberia, sometimes collaboratively, on the topic of carbon cycling. And if you email me, I will put you in touch with one or two of the best experts. I'm not sure what that person's angle was. I know there have been controversial papers on methane release from submarine sediments into the ocean and then into the atmosphere. And you have experts here in the building, in the next building over, who have been on expeditions that have addressed that specific topic. And that's methane coming from submarine sediments. Of course, there's methane and hydrates all around the world's oceans, not just in the polar regions. But you're especially important here because during the last ice age, your Arctic was a tiny little ocean, half its size, and all those continental shelves were land and covered with ice shelves and ice and compacted, and then ice melted and sea level rose. And so it's even more complicated up here. I would say in terms of the global carbon budget, the figure that was too complicated to read, that's 3 or 4 years old. You could probably catch up on that pretty quickly with a few papers. I'll put you in touch with a couple of people. But I don't think anybody knows the answer Arctic-wide, okay? That's my answer. They may say they do, but I don't believe them. I mean, there's estimates, I'm sure. That carbon budget, read Bert Bolin's papers and you'll see, and you can see how much it's changed and improved, you know, every year. But the fundamentals haven't changed that much. Next.
Don't we have some student questions here from the first rows? No? No? Is there any more? It's really hard to see from here. Is there any more question?
No questions?
No? Then, thank you for those questions that we got here. And then I leave over to Cindy, who will do the rest, right?
Yeah.
Oh, thank you.
So, yes, it's my duty on behalf of the Faculty of Science here at Stockholm University to give you this diploma in recognition of giving the 2017 Bert Bolin Climate Lecture in climate research. And some nice flowers to go with that.
Thank you very much.
And I think we get.
Thank you for a nice lecture.
Thank you, sweetie. It's been a pleasure. It's been a pleasure. I have to thank everyone here and in the Bolin Center and all the scientists and students who I know. It's a pleasure. I like a good audience. At least you didn't fall asleep, right? And I respect this because, like I said, I think I heard Bolin talk in 1976. And I, of course, knew his work because I'm really old and have followed this a long time. But you're the center of this, and many of your scientists are contributing enormous stuff on the carbon cycle, the ice, the sea level, and many other aspects. We're only just beginning to understand the polar regions. So stay in touch with those people. And thank you again.
Thank you. And thank you as well. I would like to say that there are some refreshments that are being served outside on the second floor. So when you go out, you can have a cup of coffee or something to drink. Thank you.
Thank you.